Next, we will discuss how to do calculus with the hyperbolic arcsecant of x. Let's consider the hyperbolic arcsecant of x and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. But let's not forget the alternative definition of the hyperbolic arcsecant function. We can differentiate this function using the chain rule, which is particularly easy when applied to the natural logarithm function. Simplifying the expression produces a surprisingly nice result. In summary, we now have the formula for the derivative of the hyperbolic arcsecant function, as well as the formula for the antiderivative of its derivative. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the hyperbolic arcsecant function applied to the power function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after plugging everything in and simplifying. Let's do another example. We start the process by recognizing that we have to find the derivative of a composition of the natural exponential function and the hyperbolic arcsecant, which is equal to the following expression, in which we know how to find all the components. And there isn't much to simplify here after plugging everything in. Let's do an example of an integral. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the hyperbolic arcsecant, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function back for t. Let's do an example, this time of a linear substitution. We set up the linear substitution by setting t equal to 3x and finding the differential of t and expressing dx in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. We discussed how to differentiate and integrate the functions that have the hyperbolic arcsecant as one of their components.